Hello and welcome to this video on finding various inner products. So in this video is just going to be made up of a bunch of examples. We saw in the last video, again if you've been watching, hopefully following along, I introduced you to the concept of an inner product on a vector space. Remember, an inner product was a function where your inputs were vectors from a vector space and your output was a real number or a scalar. And this function had to satisfy four properties, right? There was a property of symmetry, which is like a commutative property, additivity, which was like a distributive property, homogeneity, and positive definiteness, right? So again, if you'd like to go back over my previous video or look up what it means for a function to be an inner product, please do so. In this video, just going to be going over examples where I'm given an inner product on some vector space. I'm given a function, a rule that is, told to me that I'm told that it's an inner product, so I don't need to verify the four properties. They should hold. And then I'm just going to be evaluating an inner product for the given vector inputs, and that's it. Okay, so first example, where I'm asked to find an inner product. So say I'm given inner product on R2, this rule here, where the inner product of vectors u and v from R2 is just the dot product. And remember, the dot product on a Euclidean space, you could also call this the standard inner product, or the Euclidean inner product, pardon me, on R2. And yeah, so now let's say we're given our rule here, and again this is an inner product that satisfies all four of the properties mentioned. Now suppose u is the vector from R2, 3, 4. V is the vector from R2 with components 5 and negative 12. Find the inner product of u and v. Right, so the inner product, again, of u and v is simply the dot product of u and v. Now the dot product was simple. I multiply corresponding components and then add those products. Right, so it's first component, product of the first components, 3 times 5, plus the product of the second components, 4 times negative 12. This is 15 plus negative 48. So the value of the inner product for these two given vectors, right, the way this inner product on R2 is defined, is negative 33. And that's it. Right, the output should be a real number, and this rule satisfies all four of those properties. Again, I'm not going to show that, and I'm not going to verify that. You can try on your own to verify that this rule, this inner product, does satisfy the symmetry, additivity, homogeneity, and positive definite properties. But I should end up getting a real number when my input is any two vectors from the vector space we're given. So here from R2. And that's it. Negative 33 is the value of the inner product of this vector u and this vector v on R2. Okay, simple as that for the dot product. All right, the next one. Here I'm given an I'm told this is an inner product on R3. So now my inputs are vectors from R3, and again my output should be a real number. And here it is, right? I'm told this is an inner product, that this function, this rule, satisfies all four of those inner product axioms. So I have now again, u and v are vectors from R3, so let's say u1, v1, u1, u2, u3, and v1, v2, v3. So u1 is the first component of u, u2 is the second component of u, and so on. So the output here is 2 times u1, v1, plus 3 times u2 v2 plus 1 times u3 v3. And you see how this rule is similar to the dot product? All right, the dot product is just one of each of these, right? u1 v1 plus u2 v2 plus u3 v3. That would be the dot product if I got rid of those coefficients 2 and 3. But putting positive coefficients other than 1 on some of these terms gives me what's called a weighted Euclidean inner product. Again, this was mentioned in the previous video. This is an example of an inner product on a Euclidean space, R3, R2, whatever. So just keep that in mind, that the dot product isn't the only inner product on a Euclidean space. Right? There are infinitely many others, right, like this one on R3. Alright, so just following the rules here. I'm given vector u is the vector from R3 with components 8, 0, and negative 8. V is the vector from R3 with components 8, 3, and 16. And I'm asked to find the inner product of u and v. Alright, so the inner product of this vector u and this vector v is, and it's just like any other expression, any other function. You're just plugging in and simplifying. It's really that simple. Just got to pay attention to the rules. So it's 2 times u1. Now again, u1 would be the first component of vector u, so 2 times 8. Times v1 would be the first component of vector v, that's 8 again. Plus 3 times u2, second component of u is 0, times v2, the second component of v is 3. And then plus u3 times v3, so negative 8 times 16. Alright, so we're seeing here, this is, you see how this is 16 times 8, right? This is 16 times 8. This is 0, right? There's 0 in the middle. And this would be negative 16 times 8. So I'm seeing 2 times 8, 16 times 8 here, negative 16 times 8 over here, so that makes 0, and then I got 0 in the middle. This is 0. So the inner product of these two vectors, using this inner product, is 0. And what we're going to see in a later video, if you remember the dot product? Remember when the dot product of two vectors in Euclidean space was 0? That meant that those two vectors were considered orthogonal, or perpendicular if you saw pictures. They'd be forming a 90-degree angle if you put them both at the origin in R2 and R3. A little harder to see in R4 and R5 and stuff like that, but they're perpendicular. Well, we're going to generalize that concept in a future video to the word just orthogonal. All right, so you're gonna stop using the word perpendicular and start sticking to the word orthogonal, because depending on the inner product you're given, all right, so I'm given this inner product here for R3. If the inner product of two vectors is 0, then we would call those two vectors orthogonal under that inner product. All right, so you might say, hey, these vectors aren't, if you looked at these in R3, and I don't have a picture for you, but you're like, hey, those don't look like they form a 90-degree angle. Well, not under the dot product, right? The regular dot product, they don't, right? But under this particular inner product, they are considered orthogonal, even though they aren't necessarily perpendicular, right? The word orthogonal is going to simply mean the inner product is 0. All right, that's enough about that. Again, I'm going to get to that in a later video, so if that didn't make a lot of sense right now, I apologize. It'll be talked about much more when we get to the concept of orthogonality. But that's it. Just plugging in, playing, just like any other function. Plugging in and simplifying. All right, here's another one. This is the Frobenius inner product on R3 by 2. the inner product of, this is the space, the vector space of matrix 3x2 matrices with real entries. And it's the inner product of, matrix A with matrix B. Now notice I don't have a rule written because I've already told you what it is. All right, I mentioned this in a previous video, my previous video on when I introduced inner products. The Frobenius inner product on a set of matrices on the vector space of m by n matrices is kind of like the dot product. You just multiply corresponding entries and then add their products. All right, so let me point that out. Let me show you what I mean here. All right, so the Frobenius inner product of these two, I've got these are 3x2 matrices. Here are my inputs, these vectors, these 3x2 matrices. A is this 3x2 with 1, 2, -3, 0, 5, 4 as the rows, and B has the rows -1, 4, 0, 3, and 7, 2. All right, so the inner product in this case of matrix A with matrix B, like I said, it's the Frobenius inner product. That means first row, first column of A multiplied by first row, first column of B. So 1 times -1 plus, and you're going to see this is very much like the dot product in Euclidean space. I just multiply corresponding positions, corresponding entries, and then add those products. So first row, second column of A times the first row, second column of B, 2 times 4, plus then next, second row, first column of A times second row, first column of B. Multiply corresponding positions and add them together. -3 times 0 plus second row, second column of A times the second row, second column of B. Right, 0 times 3 plus third row, first column of A times the third row, first column of B. 5 times 7 plus, and finally the third row, second column of A, third row, second column of B, 4 times 2. Okay, so I'm getting what? -1 plus 8, all right, 2 times 4 plus 0 plus 0, plus 35, and then plus 8 again. All right, so that's, 7 plus 35 is 42, plus 8, 50. And there we go. Again, the output, right? Your inputs are two vectors from a vector space. Your output is a real number, just a number. And there you go. This is called, again, the Frobenius inner product on a set of on the vector space of matrices, right? Just multiply the corresponding entries and add those results. Just like the dot product in Euclidean space. I've said that before. Wonderful. All right. And this, again, as simple as that. All right. As simple as that. Just plugging in, and now there you weren't given a rule, right? You were it was assumed that you knew what the Frobenius inner product is, and that might happen sometimes. So hopefully you've read through your texts or whatever sections you're looking at that involve inner product, and look at what inner products they've introduced you to, so that if they ask you, find the Frobenius inner product, you'll know what they're talking about. Or find the integral inner product. This was another one that was mentioned in my last video where I introduced inner product to you. So here's another example. The integral inner product on C from -1 to 1 here, this closed interval from -1. Remember, this was the vector space of all continuous functions on the interval from -1 to 1 on the real number line. All right, this is one of those infinitely dimensional vector spaces. All right, and the integral inner product, again, is very similar, has a similar structure to the dot product. I take the inner product of two, continuous functions, f and g, functions that are continuous on the interval from -1 to 1, and I take their product and add them up over that entire interval. Now, adding up a product of of continuous functions over an interval, that's an integral in some sense. Right? So again, it's very similar. It's a similar sound to dot product. It's not exactly the dot product though. More like an infinite number of term dot product as whatever. All right, and then so that's how my inner product is defined. Again, it's going to end up with some real number, right? My input is two vectors, two continuous functions. My output's going to be a real number, and it satisfies all four. This rule should satisfy all four of those inner product axioms, and you can verify that on your own if you wish. All right, so suppose these are my two vectors, just a couple polynomials. Now, I didn't have to use just polynomials here, right? I could have used any function that is continuous over this interval from negative, so like e to the x, some exponential function, or certain logarithmic functions, not the log of x, right? That wouldn't be continuous over the negative numbers, but a transform, some shifted log function. Maybe the log of x plus 2, I could use that if I wanted to. So it didn't have to be polynomials, right? Let me just point that out. But here are my here are my vectors, right? This first function, negative x, that's continuous from negative 1 to 1, that's in this vector space, and g of x equals x squared minus x plus 2. And I'm asked to find the inner product of these two, vectors, these two functions, using the rule. Right, using the inner product on this vector space that we are given, this integral inner product. So the inner product of f and g is equal to the integral from negative 1 to 1 of f of x times g of x, right? So negative x was f of x times g of x is this x squared minus x plus 2 with respect to x, right? dx. Now again, I'll multiply this out. This will be the integral from negative 1 to 1 of negative x cubed plus x squared, right? This is just distributing the negative x here, minus 2x. And then with respect to x, and don't, hopefully you remember from your calculus class, how to do this. Antiderivative of this would be, negative 1/4 x to the 4th plus 1/3 x cubed, and minus, x squared. And we're evaluating this at negative 1 and at 1. Well, first I would plug in 1, then I'd plug in negative 1, and we subtract, right? So if I plug in 1, I'm getting simply, negative 1/4 plus 1/3 minus 1, which I'll simplify that in a second. Then I subtract from that the value at the lower limit at negative 1. Now plugging in negative 1 gives me negative 1/4, and then minus 1/3, and then minus 1. Right. Okay, so you see some things canceling here, right? With the even, the negative. You see, I have negative 1/4 minus negative 1/4. I'm distributing this negative 1 over here. You have negative 1/4 here minus negative 1/4 there. That's 0. Then 1/3 minus negative 1/3. That's 2/3. And then negative 1 minus negative 1 is again 0. So I'm left with 2/3. And that's my final result. Right? 2/3. Okay. That's it, right? My input is a couple functions, a couple vectors from this vector space. My output is a real number. Just got to know how to do the rule. Right? Just got to know how to perform integration. Or multiplication or addition or whatever's involved in the rule for the inner product. Just got to know how to do it, and it's as simple as plugging in and evaluating. Okay, and then one final example. Here's another inner product on a different vector space. I didn't do any inner products on these vector spaces last time, but here's an inner product defined on P2. Remember, this is the set of all polynomials of degree 2 or less. Where P and Q are polynomials of degree 2 or less, and the inner product of P and Q is A0, B0 plus 2A1, B1 plus A2, B2, where A0 and B0 are the constant terms of P and Q, respectively. A1 and B1 are the linear coefficients of P and Q, respectively, and A2 and B2 are the quadratic coefficients of P and Q, respectively. All right, and notice again how this inner product, this rule here, again, this will satisfy all four of the inner product axioms. You can verify that for yourself if you wish. But notice how it's very similar again to the dot product, A0, B0, A1, B1, A2, B2, only the coefficients aren't all 1, right? There are some other positive coefficients here, like positive 2. So this is almost like a weighted dot product, but again, it's not called the dot product, right? This is not the dot product. Similar, but not. All right, so suppose given p of x equals 3 minus x plus 2x squared. So that means that a0, remember a0, a1, and a2 are the coefficients of p of x. a0 is 3, a1 is negative 1, and a2 is 2, all right? And then q of x has the coefficients b0, b1, and b2. b0, notice there's no constant term, so b0 is 0, and then b1 is 1, and then b2 is negative 1. I'll just write b2. Right? So you pay attention to that. And then we just pop these into the rule for this inner product, and we'll evaluate, and it's as simple as that. Right? So what is the inner product of these two polynomials, right, of p and q? I got a0 times b0, so 3 times 0 plus 2 times a1 times b1, so negative 1 times 1, plus, and then a2 times b2, positive 2 times negative 1, coefficients of x squareds, right? And we simplify this, right? So this is 0 minus 2 plus minus 2, that's minus 4. There you go, negative 4. And that's it. I'm done. Right? And right there, in just these past like 20 minutes or so, I've gone over four examples, five examples of where I was given an inner product on some vector space, two vectors from that vector space to plug in, and then I just perform the rule, perform the operation, and the output should be some real number. And if you don't believe that they're inner products, please just go and check for yourself. Verify that these rules that were given, like this rule here at the top, just verify for yourself that the rule satisfies, the symmetry property, additivity, homogeneity, and positive definiteness. The four inner product space inner product axioms. Great, and this is it. All right, and again, like I said earlier in the video, there are infinitely many inner products that you could think that could be brought up out there. So I think 5 examples is plenty for right now. Just know that the just pay attention, right? Just pay attention to what the inner product rule is, and then what are your inputs? How am I going to use those to plug in to the inner product rule? And again, your output should just be a number, right? Just a number for these inner products, and not vectors, or the output is not going to be a vector. Sometimes these are even referred to as scalar products, right? These wedges with the p and q like this, or the wedges with the f and g or u and v like I had earlier, because they're called scalar products sometimes because the output is just a number, just a scalar. All right. So hope these examples were easy to follow, and I hope you have an easy time and enjoy practicing evaluating inner products, different inner products on vector spaces on your own. And hopefully not too crazy, not too difficult. And thank you very much for watching.